So let us begin to deal with these two questions. The first question is giving us the joint density function of x and y, and first it asks the value of the a and uncorrelate or correlate with x and y, and is independent, and then the joint density function of x squared and y squared. Finally, and let us to find out the independent or dependent of the x squared and y squared. So let me see what I need to do. First, I draw the region of the x and y. So we just make an integral of this this region we can find, and let it equals to 1. We can find that the a must equals to 1 over 4. It's over there. And then we need to find the density function of fx and density function of y. What we need to do is, if we want to find the density function of x, we need to integrate by y from the infinity to minus infinity to infinity. And because of the region of the y, we just integrate from -1 to 1, and what I get is 1 over 2. Similarly, the density function of y is also 1 over 2. Then we can find out that the expectation of x and the expectation of y is also both 0. Because of, if we want to deal with the correlate or uncorrelate, we need to find the coefficient, the related coefficients. So I decided to find the variance of the x and the variance of the y. So I also calculated the expectation of the x squared and the y squared. Both of them are 1 over 3. And also we need to find out the expectation of x times y. And what we need to do is to integrate the x and y region with xy times fxy, and what we get is just 1 over 9. Then the correlation is just equals to expectation of x times y minus expectation of x times expectation of y. It is equals to 1 over 9. It is not equals to 0, so they are correlated. And about the third question, we find that the density function of x and the times density function of y is just equals to 1 over 4. This is not equal to the joint density function of x and y, so they are dependent. For the first equation, the distribution function of the joint distribution function of x squared and y squared is just equals to the probability that x squared is smaller than x and y squared is smaller than y, and this is just because the probability of the x is between minus x and y is between minus capital Y and y, and this is just equals to the distribution of 1 plus x times y with the distributed integrate region of minus x and minus y and y. What I get is just equals to x times y. Then we take a derivation of x squared and y squared. What we get is just 1 over 4 times x times y. And x and y are both between 0 and 1. Then we need to get the density function of x squared and y squared. It is used the same way when we find out the density function of fx and fy. And what we get is just 1 over 2 times x and 1 over 2 times y. This time we find that the joint density function of x squared and y squared is just equals to the multiply of the density function of x squared and y squared. So in this time, the random variable x squared and the random variable y squared is independent. Then we come to the second questions. The second question is giving us the joint density functions of x and y and the region of the x and y. And let us to find the a and the expectation of x and the conditional expectation and the expectation of y and so on. Finally, it asks us to prove or disprove that the x and y are uncorrelated. So let we see. This time we may change the x to r times cosine theta and y equals r times sine theta. In this case, the integrate is just become the integrate is just become r from 0 to 1 and theta from 0 to 2 pi. So we can see the finally we get is a times pi equals to 1 and a equals to 1 over pi. And then just similarly with the problem 1, if we want to get the density function of x and y, we need to integrate x and integrate with y. What we get is 2 times square root of 1 minus x squared over pi and 2 times square root of 1 minus y squared over pi. In this case, we get the density function of fx and fy, so we can get the expectation of x. And what we get, you can just see on the paper, is 0. Similarly, because that the density function of x and y are same, so the expectation of y is also 0. Then we need to find the conditional expectation of fx under the condition of y. What we need to integrate is just x times the density function of x under the condition of y, and which is just equals to x times the joint function of x and y over the density function of y. And what we get is also 0. Also, the expectation of x over the random variable of the y is just to substitute the y to the capital Y. So this time it is also equals to 0. Because of the density function of x and the density function of y is the same, so the expectation of the y over the under the condition of y and under the condition of random variables of x is also equals to 0. Finally, what we need to find is the expectation of x times y, and this is very simple. What we need to do is to integrate x times y times 1 over pi, and this is just equals to it's also equals to 0. Finally, the relation coefficient is just equals to the expectation of x times y minus the expectation of x times expectation of y, and this is just equals to 0. So these two random variables are uncorrelated. That's all. Thank you very much.